Here is a combined summary of the 2 pages. The paper presents a novel algorithm, cross-source context place recognition, CSCPR, for RGB-D indoor place recognition that integrates global retrieval and reranking into a single end-to-end model. Unlike prior approaches that primarily focus on the RGB domain, CSCPR is designed to handle RGB-D data. The authors extend the context of clusters, CoCs, concept to handle noisy colorized point clouds and introduce 2 novel modules for reranking: the self-context cluster, SCC, and cross-source context cluster, CSCC, which enhance feature representation and match query database pairs based on local features, respectively. The authors highlight the challenges of place recognition, including different sensors, environmental challenges, and the scarcity of large-scale clean datasets. They argue that traditional approaches rely on global retrieval, which extracts global descriptors from each frame and ranks the database frames by similarities with the query frame. However, these approaches overlook the potential of RGB-D data, especially for indoor environments where depth information can be crucial for place recognition. The authors propose a novel end-to-end architecture that jointly processes RGB and geometric information and integrates global retrieval and reranking for RGB-D point cloud place recognition. They introduce 2 large-scale clean datasets, ScanNetIPR and ARKitIPR, which are specifically designed for training purposes of RGB-D place recognition tasks. The main contributions of the paper include a new end-to-end architecture for RGB-D place recognition, a novel RGB-D place recognition reranking method, and curated large-scale RGB-D indoor place recognition datasets. The authors evaluate the performance of CSCPR on different datasets and demonstrate its effectiveness in real-world robot experiments. They achieve at least 36.5% improvement in recall at 1 compared to other state-of-the-art RGB-D indoor place recognition methods. Overall, the paper presents a comprehensive approach to RGB-D indoor place recognition, addressing the limitations of traditional methods and providing a novel solution that integrates global retrieval and reranking. The research paper discusses a novel place recognition model, CSCPR, which addresses the RGB-D indoor place recognition problem. It's formulated as a point cloud retrieval problem, separated into global retrieval and reranking tasks. The global retrieval calculates global descriptors for query and database frames, ranking them based on similarity. The reranking model processes cross-source local features to refine the ranking. The architecture includes a self-context cluster, SCC, for downsampling and enhancing local features with global information, and a cross-source context cluster, CSCC, for capturing cross-source correlation. The training strategies involve multiple loss functions, cosine annealing, and atom optimizer. The model's effectiveness is demonstrated through its ability to capture relationships between RGB-D clouds efficiently and outperforming comparable methods in terms of computational cost and recognition accuracy. Here is a combined summary of pages 5 and 6 of the research paper. The authors propose a novel approach to RGB-D indoor place recognition, which involves 2 stages: global retrieval and reranking. The global retrieval stage uses a similarity-based method to retrieve top candidates, while the reranking stage refines the results using a correlation-based method. The authors also introduce 2 new datasets, ScanNetIPR and ARKitIPR, which are designed for RGB-D indoor place recognition tasks. The authors use a similarity-based method, called SCC, similarity-based correlation calculation, to calculate the correlation between local features from 2 frames. The SCC method downsamples point features to center features and enhances the center features by the similarities with all point features in the frame. The authors also propose a correlation-based method, called CSCC, correlation-based similarity calculation, which calculates the correlation of local features from 2 frames and concatenates the features by the correlation relationship. The authors evaluate their approach on 3 datasets: ScanNet-PR, ScanNetIPR, and ARKitIPR. The results show that their approach outperforms state-of-the-art methods in terms of recall at 1, recall at 2, and recall at 3. The authors also conduct an ablation study to evaluate the effectiveness of their components, including SCC and CSCC. In addition, the authors compare their approach with other reranking approaches, including classical ransack-based geometric verification and learning-based place recognition reranking approaches. The results show that their approach outperforms classical approaches by at least 34% and 20% at recall at 1 in ARKitIPR and ScanNetIPR, respectively. The authors also observe that their approach has less inference time than other approaches by at least 20%. Overall, the authors propose a novel approach to RGB-D indoor place recognition, which involves two stages: global retrieval and reranking. The authors also introduce two new datasets and evaluate their approach on 3 datasets, demonstrating the effectiveness of their approach. The research paper discusses the RGB-D place recognition problem, focusing on the development of a fast and effective reranking model. The authors propose an integrated mechanism for both global retrieval and reranking, leveraging the CoCs concept for feature processing in RGB-D point clouds. They demonstrate the efficacy of their approach by outperforming other state-of-the-art methods by at least 36.5% in the ScanNet-PR dataset. The paper also highlights the importance of semantic pre-training for future work to improve the model's understanding of the environment. The authors provide a comprehensive evaluation of their method, including comparisons with other approaches and a detailed analysis of its strengths and limitations. The paper discusses the creation of a new dataset for place recognition tasks, named ScanNetIPR, which is designed to be more challenging than existing datasets. The dataset differences are shown in Figure 4, where the furthest positive frame, FPF, of ScanNet-PR and ScanNetIPR are compared. The FPF depicts the least overlapping matched frame to the query in both datasets. In ScanNetIPR, the overlap is the only criterion for matching, thus it is more accurate for training and evaluating place recognition tasks. The algorithm generating training data is presented as Algorithm 1, which uses overlap to select the frames for training and evaluation. The frames are chosen by the motion of the camera, where if the current frame overlaps too much with the last frame it will be dropped. The overlap in this step is calculated by the symmetric intersection of the union, IOU, of the voxelized point clouds. The dataset is separated into training, evaluation, and testing scenarios, and each testing scenario contains database keyframes for recall calculation. ScanNetIPR contains 1605 scenarios and 53,201 frames in total. Each frame of the point cloud contains positional information x, y, z, normal information nx, ny, nz, color information r, g, b, and also semantic labels of each point. Comparisons of global retrieval in novel datasets are presented in Table IV, where approaches in ScanNetIPR have lower recall values than the ScanNet-PR dataset. This is because ScanNetIPR presents a greater challenge than the ScanNet-PR dataset because it includes pairs with smaller overlapping areas. Qualitative results are shown in Figure 5, which contains 2-point clouds in a scene of ScanNetIPR and 2-point clouds in a scene of ARKitIPR. The normals in the figure represent the normal vectors of the points, which are shown as RGB images with the NX, NY, NZ as R, G, B. The RGB-D point clouds are extracted as mentioned in section IV. The semantic information in ScanNetIPR is point segmentation and in ARKitIPR is the object classification with bounding boxes. Here is a combined summary of pages 11 and 12 of the research paper. The authors present a qualitative comparison of their approach, CSCPR, with other state-of-the-art methods, including ART2Former and Teaser++, in Figure 6. The results demonstrate that CSCPR balances geometric and RGB information well, achieving the best performance even in scenarios with small overlapping areas. In Table V, the authors provide a quantitative comparison of their approach with other methods on the ARKitIPR dataset, showcasing the superiority of CSCPR in both RGB-D and pure point cloud place recognition tasks. The results indicate that CSCPR outperforms other approaches, with recall at 1, recall at 2, and recall at 3 scores of 75.13, 80.24, and 82.33, respectively. The authors then delve into the architecture details of their approach, specifically the global retrieval block, which consists of 4 adapted CoCs layers. Each CoCs layer comprises 2 X-point conva former, PCF, and 4X context cluster block, CCB, with feature dimensions of 64, 128, 320, and 512, respectively. The PCF and CCB in the same CoCs layer share the same feature dimension. The authors employ PCF to aggregate output point features into a global descriptor with a feature dimension of 512, leveraging multimodality feature aggregation by enhancing color features with relative geometric information based on KNN neighbors. The CCB performs multi-scale feature processing by enhancing current level point features with high-level center features. The points are downsampled using FPS in the 4 layers, and the point-to-center relation is initialized by KNN and learned by the neural networks. The authors also describe the architecture of the SCC and CSCC models, which process the point features from the global retrieval and cluster them into centers with a dimension of 256. Finally, the centers are processed by correlations between the 2 clouds of centers and aggregated into a reranking score.